I'm still an engineer, even on record I'm an engineer. And today I'm going to talk a little bit about this particular project that I'm very excited about, and we've been working on that for a few years. And it is work in progress, as you will notice. And I just want to share with you our thoughts and our tools that we're trying to use to attack this particular problem. I have some results, but as you could tell, it's a very, very preliminary results. And I gave a similar talk, and Robert was there, and he got to hear the same thing again. I'm sorry, Robert. But I added a few new results just for Robert. Okay? The problem we're trying to address is all about learning about how the brain works and what can we do about it. Before getting that started, I wanted to acknowledge my group. These are my students. There are a few of them that are missing here in this picture. And these two are MDs, neurologists and neurosurgeons. Unlike the guy who was friends of Toby Berger, who wasn't a neurosurgeon, but this guy actually does surgery twice a day, and he does get into people's brains and head. And I'm only going to talk about one student's work today, and the work that I'm doing is sponsored by NSF. Surprisingly, not NIH, NSF, because it's more engineering than health. All right? And Texas Instruments, we'll find out why in a few minutes. Now, we all know that we've been interested in how the human brain works for centuries and centuries, and which is nothing new here. But what is interesting is that we are all excited about the Brain Initiative in the US, and Obama promised some funding for this particular initiative, and we're all crossing our fingers that it's going to realize and it's going to help move the field forward. But we shouldn't get too excited, because we had the decade of the brain not too long ago either. And nothing happened. And George Bush Sr. declared the 90s as the decade of the brain, but not much funding came out of that, and everybody was disappointed, right? Let's just hope that this brain initiative is not a disappointing hype. Now, what are the grand challenges that many people are talking about today, especially in response to the brain initiative? There are many, many of them. The one that I'm interested in, and my group is interested in, is sort of understanding the relationship between how a neural circuit works and how that relates to behavior. And that's sort of interesting to us, and mainly because of our background in engineering, background in circuits, and we want to know how circuit connectivity relates to behavior. All right? And particularly, the two examples that we are actively working on. One is that how we can transform our brain from a diseased state to a healthy state. That would be interesting and quite useful. And second would be how we could observe brain going from when we learn something, how does the connectivity change? How the connectivity changes before and after learning a particular task. Right? These are all, in our opinion, big challenges that are very hard to tackle. And of course, there are tons of other challenges out there in this particular arena. Now, our research focus, as I said, has to do with network modulation as a reparative therapy for diseases like epilepsy, Parkinson's, Alzheimer's. And also, as I said earlier, we are interested in finding out how the circuit is connected and how the connectivity changes. And in that particular case, we are working on, not on humans, not on a very specific animal called aplysia, which has a very simple brain connectivity. And in that situation, we have access to individual neurons, and we can look at the connectivity and teach the aplysia how to eat food, and then watch how the connectivity changes as they learn how to eat, for instance. All right? Now today, I'm only going to talk about one particular project, this particular neuromodulation project, is to deal with epilepsy. Right? Let me then focus on that. And could you remind me how much time I have left, like 5 minutes before? Sure. Thank you. Now, what is epilepsy? Right? We all know roughly what that is. Basically, it is When a patient is called epileptic when he has unprovoked and very, very frequent seizures, right? And it turns out that many, many people have seizures, but it may just happen once or maybe twice in their lifetime. But people are called epileptic if they have unprovoked and very frequent seizures. But the problem is that seizure itself doesn't have a standard definition. And there are a few definitions out there. And the one that my group is focused on is that a seizure is when a group of neurons have abnormally synchronized and hyper-excited activities, right? That is one definition of seizure. And even that definition could take many different forms. It could be quite subclinical, meaning that you won't even know, or the people around the patient wouldn't even know that the patient is going through a seizure, because they just doze off or they just go in a dazed state and they don't have any, that the usual seizure that we associate with, like muscular behavior that we associate with. Or it could be a full-blown seizure. It could be very local to one area of brain, or it could be one that is multifocal and affects multiple brain regions. For that reason, it's hard to deal with a seizure, it's hard to model it, it's hard to sort of mitigate it. Now, it turns out, in the US alone, there are 3 million patients that suffer from epilepsy. And for them, obviously, the first line of defense is medication. And if medication doesn't work, which doesn't work for 1/3 of that population of patients, then the next option is removing a part of the brain. Which you can imagine that this is not a good option. It has a lot of side effects and a lot of other sort of issues with that. Now, what people have been looking at over the last few years is stimulation as a method to mitigate epilepsy.
Which part of the brain do they usually remove for epilepsy?
Many parts are removed, mostly near the language region.
Mediotemporal. Not prefrontal.
Not prefrontal. No.
It depends on the focus.
But they do resect many regions, especially if it's focal. Now, why stimulation is promising? For one thing, it was promising for Parkinson, and people are inspired by that. And obviously, the main reason is that neurons respond to electric signal, and that's sort of the thesis on that, right? Now, we're going to focus on that, obviously, and we've been working very closely with the surgeons and neurologists that I showed the picture earlier, and dealing with this and sort of recording and stimulating, you have a few paradigms that you could try. One would be deep brain stimulation, which is, that's what they do for Parkinson, for instance. Another one would be subdural stimulation, meaning underneath the skull, on top of the brain, underneath the dura. And the last one would be on top of the head, completely on top of the head. And as you can imagine, as these are possibly 3 options of stimulation, you can imagine that these things often have to do with the trade-off between being invasive and being effective. And the thesis is that if you're not invasive at all, it's very much possible that it's not effective by any means. And it is if you are very, very invasive and you do a deep brain stimulation, you destroy some tissues along the way when you penetrate into the brain regions. All right? Therefore, what we have focused on is subdural stimulation. And basically, as you can see, a grid of electrodes have been placed on top, underneath dura, and we are focusing on that particular technology. Now, what happens today is that doctors put the electrodes on top of the brain, and they do measurements for hours and hours, and they identify seizure zones. And then the next morning, they will reset that particular region. Right? And this goes back to your question about which region they often take out. Right? And these are the electrodes that are commonly used, and there's products out there of that sort. And our concept is that to use that particular technology, not just for recording, but also for stimulation. And that's the idea. Now let's look at it for a second. Often these are 150 channels or so, and there are now newer ones that are more dense, and there are about 250 or so channels. And these are our recordings. And they could look something like this, right? And this is one example. And obviously, when you look at that, you recognize that these are not spikes, right? Because these are not recordings close to neurons. They're recording on the surface, therefore they're more like local field potentials. Therefore, they look like a Gaussian signals, right? They look like a signal as opposed to spikes. But that's what we receive. And the question then is that if these are the recordings, how could you, from that information, decide where to stimulate and when to stimulate and see the effectiveness of that, correct? And
on the,
yes?
The technology that's there, I mean, that's not symmetric, right? You got to pump energy in, and you're trying to get a deeper brain structures. The voltages that you apply are much bigger than the voltages you pick up. So there's probably some chemistry there, so you know whether that's worked out or this is just in the early stages.
It's very, very early stages.
Answered my question?
Yeah, it's very, very stages, and the surgeon that we're working with has the IRB approved for this, but we are not ready yet.
And one last thing, do you have animal models that you can play?
There are animal models out there, but we don't have that. Our colleagues want to jump right into humans, and they do not want to. But there are animal models of dogs and primates and others, and of course rodents and all that. There are papers published in this space, but our colleagues want to jump right into patients. Now, basically, this is what we envision, right? A system that you could build of this type, and the idea would be to depress, not to excite, right? Because the system is going through an excited period. We would like to prevent that. Therefore, the idea would be to depress the population from going in, so that they will not go into a hyperexcitable state, right? And what we need to do is need to be able to precisely find out when they're going to the seizure state, which electrodes are the right ones to stimulate, and do it, right? Therefore, you can imagine a system diagram like that data comes in, and there's a lot of data, a lot of connectivity and connection between these possible electrodes. You could do a spectral decomposition because there are different bands that these signals could live on. You could do a temporal decomposition to identify, in an ideal case, find out when the seizure is going to happen, predict the seizure, and then finally determine the connectivity of information, a connectivity between these electrodes, like what electrode is related to another one, not necessarily spatial relation, but signal relation. And then from all of these things, find out where the location of the stimulation should be and when the timing should be. And the thesis is that you should stimulate with a very, very low frequency signal. Right? Unlike other stimulations like Parkinson and others that we have done in our group that have to do with 50, 100, 90 hertz stimulation, here we anticipate that an effective stimulation would be in a few hertz region to dampen this excitement. Right? And that's our game plan. And I said all of that already. And we would like to do all of that. And now let's look to see what we have, right? What do we have? We have a whole bunch of time series, right? That means N is time index, right? These are our recordings. And D is the number of channels that we have. Therefore, you can imagine we have this huge matrix of data. And this N could be hours and days and all that. Not days, but hours. And this D could be 154, for instance, right? And as I said earlier, these are not spikes, these are field potentials, and they look something like that. And it would be nice to sort of see if there is any sparsity in this data, so that we don't have to compute so much, and we could sort of reduce the dimensionality of the problem quite a bit, right? And of course, idea would be to see if there is sparsity temporarily and all that, in all the spaces that you're worried about. Right? And a quick thing to do would be put the signal through a sort of a frequency decomposition and recognize that a lot of energy lives in the low frequency range. And maybe that would be a hint that we should look for connectivity and a structure here, right, in this range. And what at the end of the day, what we're interested in is this, that if these are some electrodes, some label on electrodes, then we would like to look at the connectivity of these. For instance, to say that this is influencing this electrode, for instance, right? So that if this is excited, this is going to make this one excited also. And we would like to prevent that, right? This is the game plan. And you're envisioning that the connectivity may change across different frequencies, and the connectivity may change across time, right? That's sort of what we're trying to investigate, right? Now, then this basically what we're trying to figure out first is this issue of causality. Right? Let's see what we can do there. It turns out that when you look at causality, it's not a new problem. It's been around for a long time. That we've always, for many, many years, have been interested in time series and how do they relate to each other. Can one forecast another? Right? And this has been an old problem that people have been interested in for years and years, economics, transportation, and many different fields. And it turns out that many, many sort of well-known mathematicians have worked on this problem before. Wiener himself worked on that problem, and as a result of that, Wiener filtering and other ideas came about. And Granger, as we all know, got a Nobel Prize for his work in that space, right? And it also turns out that there is a less known German professor that worked on this problem as well. And Jim Massey and others came up and expanded the concept that Granger had and came up with this concept of directed information that I'm going to talk about next, right? And that's exciting because that is a way that mutual information or information theory could help us determine causality and timing of different time series, right? And that was the idea. And then, as I mentioned earlier, it should be credited to Hans, even though he never published it, but it is in his notes and all that, right? Now let's look to see what we're talking about here, right? We talked about this today all day, that we are all interested in mutual information as a very nice concept, measuring information between two time series and all that. And some equation like this could describe that in a continuous random variable situation. And we all know what that means, but the issue is that it was never developed for a situation when there is direction, right? That means that this is invariant to whether you're talking about X or Y. It doesn't care whether you're looking at mutual information between X and Y or Y and X. It's indifferent to the directionality. But from our perspective, more importantly, it doesn't give you any temporal information, right? These two it doesn't do, right? We were never meant to do, right? Now, what you could do is follow what Hans Marco and Jim Massey and others have done and define something called directed information, right? Which is an adjustment to definition of mutual information. And the adjustment is written this way. And you can imagine that what it's trying to say here is that does this sequence from 1 to n, does it influence the nth sample or not? Right? That's what it's trying to measure. And then when you compare that to mutual information, the usual mutual information, it goes from 1 to n, not little n, right? And that's the subtle difference. Therefore, if you compare these two, that's the subtle difference. And that subtle difference is important to us, turns out to be important to us. And then if you write it another way in respect to the entropy and all that, it measures the entropy of the whole sequence and subtract what we call causal conditional entropy is subtracted from that to get the directed information between X and Y, right? Therefore, if you compare that again with this is the ordinary conditional entropy. This is causal conditional entropy. That's the subtle difference. But this subtle difference seems to make it work for us, right? Now let me give you two examples just for fun and see what you're looking at, right? These two examples, example one is this, right? It's very simple. X is equal to y plus zn. Zn is noise, Gaussian or whatever, and these two are assumed to be independent, and that's what you observe. and everything is nice and Gaussian, and you would like to know what's going on and what is the causal information, direct information between x and y. It turns out that in this example, these two are the same, and they're the same as the ordinary mutual information in this particular example. Now, example 2, of course, is more fun because it's written slightly differently, and xn is written as yn minus 1 plus zn, all right? If you have the same similar things here, but then these two are independent, and then but if you write it this way, you can say that y influences x, causally influences x, but x doesn't causally influence y, and that's the difference, right? And in Gerhard Kramer's thesis, there's a whole bunch of properties and equalities and relationships between direct information this way, that way, and its relationship to regular mutual information is all been discussed and written there. But keep in mind a couple of things, that they did all of that work to be able to understand how networks with feedback work, and many of their work had to do with discrete time binary sequences, not continuous time and all that. But extensions to continuous time, as we have looked at, as we are interested in, is obviously not that hard. It's subtle differences, but not that hard, right? And that's the highlight of this example, that how it's different. Now back to reality again. The reality is the channels that we had, all right? And these are some typical numbers, typical recordings that we get, all right? And you could imagine that this particular electrode or this particular electrode is not experiencing much of a seizure, all right? But I'm guessing that here they may have gone into seizure, for instance. This particular electrode may be experiencing some seizure. And as I said several times already, it is not that hard to detect when we are in seizure or not, all right? There are many different measures you can do that. What we are interested in is finding out which electrode is experiencing seizure. Not that hard, but more importantly, we want to know which electrode influences which other electrode, which is harder. And of course, prediction of seizure is hard, right? And when we talk to many of our colleagues, they say, don't even try. Prediction of seizure is hard. Don't even go there, right? But of course, we don't know enough to be scared, right? Now, unfortunately, this is not showing up nicely. You may be able to see some extra lines here showing that this is estimation of entropy of a whole bunch of those electrodes. But I'm really sorry, but you cannot see that because I faded it too much, all right? And there are a whole bunch of electrodes here, that their lines are here, and this is the average of all of those entropies, right? And the idea here is that these are all experiencing seizure, and this is most likely the length of the seizure that this particular patient is experiencing. And the point is that the entropy, which was a piece of the directed information, has some nominal value, but as seizure happens, it rises and then goes back down after the seizure is over, and then goes into a quiet stage after seizure. Right? Now, you can imagine that this could be a way, if you have 151 channels, and it's very hard for now to compute directed information and timing information between all of those 151 channels and the relation between them. This may help us identify a set of those electrodes and focus on those. Therefore, we use entropy as a way to focus on a few electrodes. Therefore, with that plot and focusing on the ones that showed an increase and then a decrease in entropy, we went down from 150 to 25 channels, for instance, having some threshold on that. And now here also you're watching the entropy, but not versus time, but a PDF of the entropy. And we are looking at that before seizure, during seizure, and after seizure, right? Basically showing that when there is seizure, the entropy is very high, and before and after, it goes down, all right? It's for one particular patient. And this could help us have a very coarse temporal information about when seizure is happening. This could be an interesting measure, and we've used that. And all of these things done and giving us coarse measure of timing and a focus on spatial focus of electrodes, now we are ready to attack the problem that we're interested in to see if that's a feasible problem or not. And let's go back to the real data again. And for now, we're going to make an assumption that the data follows a moving average AR kind of model, because that makes computation of the direct information easier. At the same time, we're working on more non-parametric approach to computing mutual information. It's doable, but we don't have results on that yet. And with that particular computation, particular assumption, therefore this could be the underlying model, focusing on 6 electrodes, and let's say see direct information between 5 and 6. We can compute that based on this particular model. And then this could be the matrix of the direct information calculations. And this, for instance, is this particular line here, direct information between node 5 and node 6, for instance, as an example. And if you focus on a few of them like this, then you could say, is this really there, or is this because of this indirect link, right? Fair question. All right, you can do a little calculation and do a conditional directed information given x5, and then recognize that they equal to 0 actually, right? This way you can prune your relativity quite a bit, and we have done all of that. And for instance, we had just plotting out a few of these electrodes, and these are the connections between, or directed information connection between all of them. And then if you take out the one that we just talked about, the indirect information flow, it becomes a lot sparser, all right? Again, I'm sorry you cannot see, but you can see it, I guess. I guess you can imagine that there is a line between these two arrows, right? All right? And this becomes a little bit more sparse after you take that. And then you could also view that at different times. At one time, this could be the connectivity, and at different times, the connectivity could be quite different. We have noticed that as well. And also, spectral variations are there as well. Therefore, in some band, this could be, in this band, this is the connectivity, and then you could do the same indirect reduction of indirect links, and then make it a little bit more sparse like that. Now, yes?
You briefly had something that looked almost like dynamics up there. Do you have to assume that there's some sort of stationary linear Gaussian system underlying this to interpret these?
To calculate, not interpret necessarily, just to calculate. For now, our calculation is based on the assumption that the data follows that linear model.
And
right?
that it's stationary.
That is, well, yeah, stationary because of the fact that
there were no affine terms, so you subtracted off.
But remember that we have windows, right? We don't look at it forever. Right? Now, as I said earlier, we are not happy with that ourselves, right? Now, the next step, which is, sort of a very sort of natural step, is to have a non-parametric estimation, so you don't have to confine yourself to a linear model of the data. Right? Stationarity is still going to be an issue. Stationarity is still going to be an issue. I think that is harder to get away from. Therefore, we're always going to have windows and then, moving windows like that to calculate the information. Now, even the entropy information that I showed you, it was windowed, right? It was windowed, and then we moved the window around.
And eventually, if you close the loop, the control loop, then I guess you change the stationary distribution.
You live with your window, right? Basically, you're imagining that just like many other control system type problem. You have a window, you make an observation, and you use that information to feed it back, and then it would be a loop, and then, I'm sure...
You can't stimulate and record at the same time, I suppose, in these grids.
The doctors believe they can. I'm not convinced. They believe they can, but I'm not sure whether their engineering skills are.
You can do it with transcranial. Yeah, they can stimulate and record at the same time.
Yeah, but we are going subdural.
I know, right?
Yeah. We have a very limited equipment in that space. Right?
Logically, that's been done in intracellular. You have switching circuits that record most of the time and stimulate from time to time.
So, in in transcranial, the stimulation and the recording are different.
Yeah, transcranial is magnetic stimulation and
Yeah.
electrical.
Exactly.
Bottom line is that we haven't gotten there yet. All right. Now, just to finish up, basically, where we are is that we are interested in using this particular sort of directed information to help us identify. It already helped us identify connectivity and directionality and all that, but we haven't gotten to the point of timing yet. The information is there, the method does provide you with information, but we haven't gotten there. One of the problems always is that the data is horrible. The data that we are given is just horrible data, and it is extreme. It is a typical experimental data that you do not generate, or you do not record data yourself. You get data from somebody else, right? There's always a problem that we have unusual recordings, and we need to deal with all of that, right? But then the spatial focus is there. What we are missing is prediction. What we're missing is fine timing from the information. But once you have that, building up a system like that is not that hard. We've done these things in other contexts before. And in fact, we work closely with the folks from TI. This monster here is a TI evaluation module board that has 4 ARM processors and 8 DSPs on this board, and is maybe 20 years ago, this computational powerhouse was filled out the whole room, but today is on this board, and actually this is just evaluation board. The chip is right here, right? Very small, and this is what we are using to crunch the data and turn it around all that, all right? And I mean, I'm not envisioning that this is going to be attached to a patient, but this is just a, sort of step one of our hardware development to solve this particular problem. But this is a very nice platform that has a Linux environment for programming and for working and partitioning between ARM processor and DSP. It's going to be a very nice platform for our students to help build the system. And of course, who knows, 2, 3, 4, 5 years down the road, we may be ready for some clinical trial, which obviously we are not going to be involved in it ourselves, but the doctors will